Welcome. In this video, we're going to discuss one aspect of computer networks and computer communication, referred to as DNS. And we're going to explain the reason for this and a little bit about how it works. The idea is that when one computer wishes to communicate with another computer, say you have a browser and you'd like to communicate with www.google.com, that name of www.google.com is not what's used as your message is routed through the internet. That name must be translated to some kind of an address, something referred to as an IP address. So DNS is the framework that's going to provide for that capability. So we'll give an introduction to that system and that architecture in this video. Modern network applications follow one of two common approaches when two machines must communicate with one another. Each of these approaches have different types of applications for which they're well suited. The two approaches that I'm thinking of here are client-server architecture and peer-to-peer architecture. In our discussion in this video, we'll be focusing on the client-server architecture. So let's clarify what this means, how this is organized, and the roles or functions of the participants, the client and the server. First, what we note is this communication is going to involve two hosts or two end systems. One of these we'll refer to as the client machine, and the other we refer to as the server machine. Now, I've placed machine in quotation marks here because in one sense, when we talk about client and server, we are talking about the physical computer devices that are communicating across the network. But we'll expand on this definition of client-server in just a bit. Let's look at an example. Suppose we have a web browser that wishes to access or request some web page in the custody of some web server. What happens is the client initiates the request. So the conversation begins with the client. The client sends a request to the server. What does the server do? The server is sitting there waiting, receives the request, and responds to the request, sending the web page that was requested back to the client. In this scenario, clients do not directly communicate with one another. The client communicates with the server responds to the client by sending some kind of a response or message back to the client. The server has some other important characteristics here. The server is always on, and what this means is it has a fixed or well-known address called an IP address. And a client can always contact the server by sending some request, sending some packet to that server's IP address. Some applications that we might see that employ a client-server architecture would include the World Wide Web or web applications, FTP for file transfer, Telnet, and email. These all follow that basic architecture of client and server. Now, we mentioned the idea of two machines communicating, but in reality, what we have is some application is running on each machine, and that application is represented as, say, some process. So we can say the processes are actually what are communicating. A process can be thought of as a program that's running within some end system or host. So the network consists of pairs of processes that send messages to each other. The client process, kind of a program running on the client machine, is what's sending the request, and the server process running on the server machine is what responds to the request. And again, in the context of some kind of communication session, as we pointed out, the process that initiates the conversation is the client, and the process that waits for a request for service and responds to that request is referred to as the server. Another important software component that is going to reside on both end systems involved in the conversation is something called a socket. Any message that's sent from a process on one end system to a process on another end system has to go through the underlying network. We saw this idea as we looked at our example of a client-server application with a web browser talking to a server communicating back to the client. In both cases, the message was sent through the network. The process is going to send messages into and receive messages from the network through this interface referred to as the socket. So this is how we kind of have an on-ramp to this network structure, the internetworking, and an off-ramp coming back to the application. So this is how we get messages into the system and receive messages from the system. So a socket really is what we call an API, or an application programming interface, between the application and the network. In this figure, we see that a socket can be thought of as a passageway between the application and the network transport layer. The application is actually pushing its message into the socket when it sends it to the other process, and it comes up through the protocol stack, through the socket, and is given to the process on the receiving side. So an analogy for what's going on here is, let's suppose we consider a building. We can consider a socket to be a door, kind of an entryway to the building. Sending processes kind of shoves the message out the door and then relies on the transport infrastructure on the other side of the door, which is really the network framework, to actually deliver the message to the socket on the receiving process. Once a message arrives at the destination host, the message passes through to the receiving process's door or socket. The receiving process then acts on the message. An example of this might be if you were running an SQL query against a relational database. The query is sent from a client to a database server. These sockets are involved both on the client machine, communicating with the client process, and the server machine, communicating with the server process. When two processes are communicating over the internet, and one process wishes to send a packet to a process running on another host, we have to provide the address of that receiving process. Now, to identify the receiving process, two pieces of information are necessary. The address of the actual machine or host on which the process is running, and the identifier that indicates the receiving process within that host. The host address is what we call an IP address. The process is identified through a special value called a port number. In our videos for computer networking, we're using the internet as our networking example. Therefore, in the internet, a host or end system is identified by an IP address. Now, with respect to the process identification, the sending process also has to go further than just saying it's on this machine. It has to provide the socket information in terms of the port number. So each socket has a socket number or an address consisting of the IP address of the host and a 16-bit number that is local to that host. This is the port. Now, popular applications have been assigned specific port numbers. This is what we refer to as well-known port numbers. So we've got something like for HTTP, for web applications, the port number is known to be 80. Using a mail server process, if we're using SMTP as the protocol, this is identified by port number 25. A list of the well-known port numbers for all Internet standard protocols can be found at the web address given here. But that still raises the question, how do we know what the IP address is? So how do we actually find the IP address of a host? That's really what we want to focus on in this video. We've been building up to this. We're going to be talking now about the DNS, the domain name service, how this actually works. Remember that as we write applications or we use applications, we may know the name of the host, such as www.google.com, but we don't necessarily know the IP address. And the IP address is what's used as messages travel across the internet, travel through the network. So how do we get the IP address? Well, DNS is a system that provides a mapping of names or host names or domain names to IP addresses. So an application that says, hey, I'm going to talk to google.com calls a service of DNS by invoking a library procedure called the resolver. And it says, here's the name that I need you to look up and return to me the IP address. So the resolver will send a query containing the name as requested by the application program to what is referred to as the local DNS server. The local server looks up the name and returns a response containing the IP address to the resolver. Now that sounds rather simple, but given the architecture of DNS, this may actually involve communicating with several servers. The idea is that there is no single entity in the internet that has a list of all the names and all the IP addresses. There is not a single source that has all of these mappings. What we have to do is work with what's called a distributed database. Parts of the mapping information might be in one server, other parts in another server, and so forth, and we have to kind of work our way through that. Fortunately, we don't have to do that. That's what DNS does. But when we say that we contact the local DNS server and it simply says, here's the address, that DNS server may have been involved in initiating a series of queries through the DNS system. So when an application program needs to translate a name, the application program effectively becomes a client of this naming system. The client sends a request message to the name server, which finds the corresponding address and sends a reply message back to the application, the client. So the resolver returns the address to the client. The query and response messages are sent using a network protocol called UDP, and these are contained in a special format packet called a UDP packet. Now, the IP address is then made available to the application, and the application then can proceed to do something like a TCP connection to the host that it wished to communicate with and carry on a conversation. As we noted, DNS mapping information is stored in a large database, in fact, a distributed database. So to manage the complexity and size of the database, we see that it is broken up into different segments. For example, there's something called domain name space, and this is divided into several categories of what are called TLDs, or top-level domains. Actually, hundreds of these have been defined, and each domain can then cover many different hosts. So each domain represents some particular service or meaning, and can extend down to what are called subdomains, and this forms a hierarchical domain tree. A TLD can be classified as generic or as a country code. Now, for the internet, the top of the naming hierarchy is managed by an organization called ICANN, the Internet Corporation for Assigned Names and Numbers. So TLDs are run by registrars appointed by ICANN. So to get a name, it requires going to a corresponding registrar to check if the desired name is available If there are no problems, the requester can then pay the registrar some annual fee and then is awarded the name. So here's a list of top-level domains. You can take a quick look at that. The comment I want to make about these is that the domain names are case insensitive. Now let's look at how DNS is actually used. Suppose you have a browser, which is our HTTP client, and it runs on some host, and it requests a URL such as www.someschool.edu index.html. To send an HTTP request message to the web server, www.someschool.edu, this host running the browser has to first find out what is the IP address for this host name. The sending host runs on the client side the DNS application, invoking the resolver. The browser extracts the host name from the URL and passes it to the client side of the DNS application. The DNS client sends a query containing the host name to a DNS server. The DNS client eventually receives a reply, which includes what we were looking for, the IP address for the host name. The browser receives this IP address from DNS, initiates a TCP connection, because this is how HTTP works, and uses port 80 at that IP address. Here's the general design of DNS. What we see is if a client wants, for example, to resolve the name www.amazon.com, it queries first the root server to find a DNS server that services .com, that top-level domain, and then queries the .com server. This is at the second level. This is the TLD, and it gets Amazon.com's DNS server, and then it queries Amazon.com's DNS server to get the address for www.amazon.com. So at the three levels, we're seeing the root server, we're seeing the TLD servers, and then we're seeing what are called authoritative servers. The root, top-level domain, and authoritative DNS servers all belong to the hierarchy of the DNS servers. The local DNS server does not strictly belong to the hierarchy of servers, but it is critical in terms of the operation of DNS name resolution. So each internet service provider, such as a university or company or residential ISP, has what are called local DNS servers. And these are sometimes referred to as the default name server. So when you're using the services of an ISP and you need to have the name resolved to an IP address, it's the default name server that is going to start the ball rolling. So when a host connects to an ISP, the ISP is going to provide the host with the addresses of one or more of its local DNS servers. Here's how the name resolution works with a little diagram to illustrate the concept. So the requesting host, which we see in the lower left corner of our diagram, wishes to send a message to the destination host, indicated in the lower right corner of our diagram. The requesting host knows the name, perhaps it's something like orders.somebusiness.com, of the destination host, but we need the IP address in order to send our packets through the network. So this is where DNS is coming into play. In the DNS name resolution process, two types of queries are involved, something called a recursive query and something referred to as an iterated query. In the context of a DNS query, recursion refers to the process of a DNS server querying other DNS servers on behalf of an original DNS client request. Iteration refers to the process of a DNS client making repeated DNS queries to different DNS servers for the purpose of name resolution. So in an iterated query, the contacted server replies with the name of a server to contact, basically saying, well, I don't really know this, but here's somebody who you can go to get the answer you want. So a query presented by a host, the requesting host, to its local DNS server is said to be a recursive query based upon the definition we've just given. So this query asks that server to obtain the mapping on its behalf. The subsequent queries issued by the local DNS server to a root server, to a TLD server, and to an authoritative DNS server are said to be iterative, since the replies to these queries are directly returned to the requesting local DNS server and not the originating client, the requesting host. It is interesting to note the changing role of client and server in this scenario. Originally, the requesting host plays client and the local DNS server plays the role of server. But in the subsequent iterative queries, the local DNS server shifts the role to that of being a client as it contacts the other DNS servers. As the local DNS server finally responds to the request from our host, it returns to the role of being a server. The process we just described of sending a DNS query and getting a DNS reply can be quite involved. So what we'd like is to have some way to improve the performance of this. And this can be accomplished through something called DNS caching. So when a DNS server receives a DNS reply, for example, the idea of mapping a host name to an IP address, it stores that information in a cache in its local memory. Then subsequently, should the same request arise, what happens is we don't have to go anywhere to get it. We don't have to go through that whole process. We have the answer locally. So if a host name IP address pair is cached and another query comes in, we avoid going through that whole complex query process that we just described. So hosts and mappings between host names and IP addresses is not permanent. It's something that could change over time. So this has to be taken into account when the cache is being used. So what happens is, after some period of time, the value that we have in the cache might become questionable because perhaps this mapping has changed. So the local DNS server has to have some way of indicating that after a period of time, we want to discard this, and then we'll go through that process again. This is referred to as the TTL, or the time to live. It's kind of a timeout for a cache entry. So the entry will at some point be discarded from the cache. And this is something that we can actually find within our search of DNS information. And we'll do that a little bit later. Now, the next thing we want to talk about is something called a resource record. So when a query goes out to the DNS system, what we're going to see is a resource record is going to come back, possibly multiple resource records. So the DNS servers that effectively implement the DNS distributed database store these things called RR, or resource records. And these would include such things as the host name to IP address mapping, but they include other things as well. So each DNS reply that comes back is actually going to be carrying one or more resource records. So let's take a look at what would be in these records. So a resource record is said to be a 5-tuple. The 5 elements that comprise a resource record would be things like domain name, time to live, class, type, and value. Let's take a closer look at each of these elements. The domain name tells the domain to which the record applies. Many records may exist for each domain, and each copy of the database holds information about multiple domains. This field, as we note here, is the primary search key used to satisfy queries. Time to live, or TTL, indicates the, say, stability of the record. Highly stable information, where the mapping, for example, is not going to change for a very long period of time. This is indicated with a large value, such as 86,400 for the number of seconds. Highly volatile information, something that is apt to change relatively quickly or after a short time span, may have a value such as 60. But this element is what comes into play when we consider caching. Class might not be as meaningful, but for internet information, it's always going to be in. For non-internet information, there are other codes that can be used. Type, on the other hand, tells what kind of record this is. Remember, we said that there could be multiple resource records that are returned in response to a query. So the type is going to indicate what kind of a record this actually is, the nature of the information contained within the record. And we provide a list of them here. A few of them that might be interesting would be A, where A is an IPv4 address, 4 A's indicating an IPv6 address, MX indicating a mail server, and NS indicating a name server. The meaning of name and value are dependent upon the type of record. For example, type equals A. In that case, name is going to indicate the host name, and value is the IP address for that host name. Where type is equal to NS, then name refers to a domain, and value refers to the host name of an authoritative DNS server that knows how to obtain IP addresses for hosts in that domain. When type is equal to CNAME, value is a canonical host name for the alias host name. When type is equal to MX, value is the canonical name of a mail server that has an alias host name of name. Sometimes the actual name of a host might be difficult for people to remember. This actual name is called the canonical name. An alias host name that is easier for people to remember can be associated with the canonical name. The messages sent between communicating hosts are contained within packets. When dealing with DNS, there are two kinds of messages. There's a query message and a reply message. Our figure here provides some information about the structure of the message. The same format applies to both query and reply messages. First, there's a header section that consists of 12 bytes. So this will cover the identification, various flags, and some other information. Now, the flags are such that the flags indicate what type of message it is. Remember that DNS messages take the same structure, but one could be a query, one could be a response or a reply to the query. So one of the flags is going to indicate the nature of the message. Also, we talked about the types of queries that could be performed, iterative and recursive. So there's information within the message to indicate whether recursion was applicable or permitted. Furthermore, we talked about the idea of accessing something from a cache versus getting it from an authoritative server. So there's an indication to that effect as well. So there's a lot of useful information here. In terms of the additional content, not just saying what we have in terms of flag bits as indicators, the remainder of the message structure is briefly described here in this figure. Well, in this video, we introduced the domain name system. We looked a little bit at how DNS works. We looked at the architecture. As we went through the details of the operation of DNS, we looked at two different types of queries. We looked at iterative and recursive queries. When using a packet analyzer such as Wireshark, we could actually look at the message formats and examine the content of messages sent from a requesting host and received by that requesting host. We can't see everything that has happened with respect to all of the iterative queries where we're contacting the root server and a TLD and authoritative servers, but we do get the result from the local name server contacted by the requesting application. So in our next video, we'll examine some of this in more detail. We'll look at a couple utilities that will allow us to interact with DNS and submit requests and receive some of the records, and then be able to examine those.